As a concept for measuring incidence, we're going to use a highway and try to measure the incidence of traffic accidents along the highway. Now for our highway example, I have here marked out on graph paper 0, 5, 10, 15, 20, etc. up to 75, so that I can actually mark the amount of space, length, which also, knowing Einstein's relativity theory, is equal to time. Now it would be really convenient if we wanted to measure auto accidents on this particular highway if all the cars started at the same time at time 0 and they just started to roll along as such, and then we just would clock the number of accidents as they go by between 0 and 75. Boom, there's an accident. Of course, the guy doesn't even stop to see if everybody's okay. And then what we would have would be one accident that occurred at 50 and 1, 2, 3, 4, 5, 6, 7, 8 cars that made it all the way to 75. So 8 cars went from 0 to 75. Our starting person time or space would be 8 times 75, and that'll equal 600. We have 8 divided by 600 per day, let's say, or per hour. Maybe that's how many cars went by in the 1 hour. Then we had the 2 other cars that went from 0 to 50 before they got into an accident. So that would be 2 times 50, or 100. We would add that to the person time. Plus 100 equals, of course, 700. So our total space-time contribution of all cars at risk of an auto accident was 700. We could call it meters, or we could call it minutes. Doesn't matter as long as you have the unit attached to it. And then our incidence out of that was 1 auto accident. So 1 divided by 700 equals 0.0014, or 1.4 per 1,000 per hour, or per minute. And that is our actual incidence. That was an example of measuring incidence for a steady state population. That is, 10 cars that started at point 0 and moved across 75 units of space-time. And we had 1 accident that occurred at unit 50. So therefore we were able to calculate the exact incidence per space-time unit per 1,000 vehicles. But in real life, highways, cars don't all start at point 0 at the same time and continue on to the 75 or their destination at the same time. There are cars on the highway all the time, just at different densities. So if we start here, we see we've got some cars moving along. More cars come in across the 0 point. Some cars merge in along the middle. And more cars start and come along. And some cars will exit early. While others continue to merge in the middle, like so. Oops, another accident, which then leads to someone coming over to try to help. Turns on the flashers, but of course somebody isn't watching, and boom, you've got another accident. Meanwhile, this one came off. This one comes on and just stops right there. So very little amount of space-time accrued with that one. Now people are stopped and slowly getting around as these guys deal with their issue. Fortunately, the first aid car is now here. So they're going to pull over ahead. They gave in some amount of time. And then at this point, we simply decide to stop. What happened here? What happened here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cars went from 0 to 75 completed without coming into any accidents. So we start with that, and we take 11 times 75. For the first part of our denominator is 825. Now, in addition, we had these two cars that came in later and went all the way to the end. But they came in at 33. So 75 minus 33 will be 42. Times 2 is going to be 84. So I'm going to add 84 and get 909. Now we also had these two cars start at the beginning and then exit at 65, as well as the truck driver that came to help and the first aid car that came to provide help. So these four cars are also going to contribute 4 times 65, which is going to be 260. So I'm going to add in plus 260 units. So we have a total of 1,169 car time. But we also have this car that went from 0 to 15, so I got to add in 15. This one that went to 30. This one that went to 45. And this one that went to 70. But we still have the 4 cars that were involved in actual accidents. We're going to conveniently say that they all happened at 45. Plus 180 is our total observed car time within 0 to 75 over the period of time, let's say 1 hour, that we observed this highway. And we have 4 accidents. Sorry, we have 4 cars involved in accidents. We only have 2 accidents total. I have 2 divided by the total amount of car observed time prior to any accident. I put it in a spreadsheet here so you can see. If you recall, we had 11 cars that made it all the way across the 75 time or space units, leading to 825 observed units. We had the 4 cars that got into accidents at 45th unit, so that equals 180. 1 car just went a little bit. Another single car went a little longer, 30. There were 4 cars that went a total of 65 units, 2 cars, a total of 42, and then 1 each for 45 and 70. So I multiply column A times column B, each one, to get the totals there, and then sum it. And this is our denominator. 1509 is our observed car time or units, whether it's time or distance, does not matter as long as you keep the units intact. And then we are going to take our total number of accidents, which were 2, and we're going to divide by the observed time, so that would be 2 divided by the sum, and our answer for incidence is 0.00133, or 1.33 accidents per 1,000 cars per hour was what our assumption was, that we observed the highway for 1 hour. And that is how you can use a highway as an example of incidence for both a steady state population, when you had simply all the cars start at point 0 at the same time and you observe them across, which of course doesn't happen in real life except in NASCAR, or the real life situation where you have cars starting at different times, cars that are already on the highway and are observed for part of the distance, cars that are coming onto the highway and only go part of the distance, and other cars that go the entire distance, and other cars that only go part of the way until they get into an accident. And this is the exact same concept we will use for calculating incidence for diseases. If you are trying, for example, to calculate how many people in a classroom become afflicted with a certain condition, you must start with the total number of people over the observation time. And any classroom, there will be some students that are not there every day. Some students will be there every day. Some students will be there for a little while and then come down with the condition of interest. And so you use all of the observed times when the subjects are at risk for the condition. You add those up. You sum those to get your total observed person time. And then you simply take the number of new cases and divide by that. What can get more interesting is when you have a condition where someone can be at risk for a little while and then not at risk for a while because they went to an endpoint, but then they later become at risk again. In our car example, we used the assumption that once a car was in an accident, it was taken off the road and towed away to the shop. Now, in fact, you might have just some fender benders where the cars stop, driver's licenses and information and insurance are exchanged, maybe the police come, fill out a report, and then those cars can both drive away. Well, if that happens, once those cars are back onto the road, they are now at risk for another accident. And so you would not exclude the additional observation time if they returned to the road. Likewise, if you're studying something like influenza, and you have somebody come down with the flu, you stop the initial observed time when they get the flu. Now, a month later, hopefully, they will be entirely recovered and they go back into that population. Now, if you are simply studying any contraction of flu, that person is now at risk for one of the other strains of flu virus that might be in the environment. So now you have to start observing and including their new amount of person time during whatever observation period you have, if that subject is back within your observation time window. So it gets pretty tricky. You do have to, in some cases, really start keeping track of every single subject in your population, not only how much time you observe them, but how much time you observe them when they're at risk, when they reach an endpoint, when they re-enter at risk, etc. Whereas some individuals, let's say they're in the classroom for the first month of the year and then they get their flu vaccination, they might be at risk for flu for another few weeks, then you would decide they're no longer at risk for flu after that. Any of the flu strains, because the vaccination includes the 3 most common or likely strains that one is going to get in that area. Now, if in fact there are 5, 6, or 7 different flu strains wandering around, and then that person is susceptible to 4 out of the 7, but not 3, it gets really complicated. We're not going to have to worry about those kind of things in our introductory to epidemiology course. The important thing is the concept of determining, even if it's arbitrarily, as long as it's reasonable based on biology, determining when a person is at risk and not at risk, and making the appropriate observation time to get your exact denominator. That concludes our example of cars, commuting cars on the freeway